Hello friends, I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A BE in civil engineering from National Institute of Engineering Mysore, a MTech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed. In this section, we'll discuss about the design parameter that has to be supplied to STAAD Pro. You can see in my background there is a physical model which I have created just to explain how the effective length factor should be applied physically. I've seen many people are still confused how effective length factors are to be applied to a structural model. So I thought a physical model would be best to explain the procedure. So before that, I will just give a theoretical brief and then we shall go to the physical model. In this model, my colleague Mr. Shel Kumar has helped me a lot in the creating the model. I thank him for that, and he has also helped me during the preparation of the video while I described the defined design parameter in the video. Before I move to the design parameter, I'll go back to the last section to the load combination. See, there is an anomaly in the code itself, IS 1893 2016 part 1. So if you look at the code, what does clause number 6.3.4 says? Combination to account for 3 directional arc with ground sharing. See, it considers ELX 0.3 ALY, 0.3 LZ, ELY and LZ. Its vertical direction is also. So point ALX 0.3 ALY 0.3. But at the last lines of this section, it doesn't consider ELZ in full. See, 1, 2, 3, 4, 6 cases are given. So whereas there is a case where ELZ full has to be considered in the this line, if you see, this line, if you see, okay. But at this part, it doesn't mention the ELZ part in totality. Or some structural engineer may demand that earthquake forces in vertical direction should be considered in full. So accordingly, the additional load combination, as this table I am showing now, you can implement this load combination in the STAAD Pro template file. I have already discussed this in my book, Design of Steel Structures with STAAD Pro, which is published in the website www.designsteel.in. So this will be the load combination. See, I have considered RQY in totality here. In totality are 1.2, 1.5, 1.5. So QX and QZ taken as 30% with the respective limited state factors. So you can take reference from this table and include such ad hoc required load combinations if you feel so. Let us go back to design parameter again. In design parameter, yield stress for 20 mm or above, the yield stress is lesser, that you have to refer to the code. So for hot rolled and welded section in STP has to be defined in STAAD row. For cylinders ratio, STAAD takes default value as that of for gravity load, but for you can define the cylinders as the condition may exist. So a member carrying compressive load resulting from greater imposed load is 180. Then compression, a member subject to compression force resulting only from combination with wind and earthquake, 250. Then compression flange of a beam against lateral torsional buckling, it's 300. Compression, member acting normally as a tie, 350. Then tension member, and for pre-tension member, that is usually which are always in tension, like rod basing, there is no predefined cylinders ratio requirement, so you can bypass the slenderness checking requirement by providing a bypass command in the STAAD Pro. That is -1. I'll show when we'll apply to slenderness ratio factor while in STAAD Pro. So next is effective length of compression member. You must remember this table: non-sway frame, non-sway frame, sway frame, non-sway frame, sway frame, sway frame. So this is a non-sway frame. This is a cross bracing. This is a sway frame. This is a moment resisting base. Is a sway frame. Now note that when a portal brace like this is added to a frame, suppose this is released, 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 this is released. So, and this as a portal brace. So for all practical purpose, you can take these members as restraint against sway because the restraint is provided by this portal brace. So you can apply the effective length factor accordingly, and that is 1. So usually most of the cases this suffice, but the cases may arise when you have to go for a rigorous analysis. To do that, you can make a simple model, plane frame model, and just see whether the frame requires a P delta analysis or not. You can run the model for a secondary analysis and see if the lateral deflection in the second order analysis, if it exceeds by 10% from the lateral deflection that is obtained from the first order analysis, then a P delta analysis is required, or a direct design method can be applied to design column like this. Discussion on such analysis is not covered within the scope of this tutorial because that itself is a big topic. So you need to remember this effective length factor. This can be about the major direction or the minor direction. Now let us discuss these factors with respect to some examples. See, this is the possible cases. KL is 0.65, L1 0.8, L1 which is pinned at bottom. I have given the which case exists here in this figure. This is available in my book as well. You can note it down from this figure as well. this is the unstable frame. But this is the case where I have talked about AIC provisions in my book. So for this column we can take KZ, K is equal to 1, K is equal to 1 if delta is not greater than 1.1 delta of first order analysis. First order analysis. Here I have discussed what is the pin connection and what is movement connection. See, this is pin in only one nail is here. Even a slight push will cause the failure of the structure. But for this frame, this will simulate the behavior of a movement connection only. It will require an adequate force to cause the failure of the structure. The next is when a secondary member will provide lateral resistance, the resistance to the compression flange, and torsional resistance to a main girder. So see that if the compression flange is the top, obviously the connection plate is very near to the top, so it will provide both torsional resistance and lateral resistance to the top flange. See, for lateral resistance, the resistance must be near to the flange, but for the torsional resistance, the level can be at anywhere. This is explained in AIC code. So for further detail, you can refer to AIC code or you can go through my book. So now this bottom flange. Now this bottom flange is compression. See, this connection plate is not very near to the bottom flange. Now if the bottom flange is compression, the depth of this connection plate from the secondary member must be more than the half of this depth of this member. Then only we can consider this compression flange as resistance again in lateral direction. Obviously the torsional resistance will be there. So this distance, this connection plate must exceed half of this depth of the main girder. A bit on flange bracing. See, some angle members are usually provided to the flanges from the girds or the purlins to provide resistance to the compression flange against lateral direction as well as a torsional resistance. So flange provides resistance to the compression flanges, but at times we may have to check the adequacy of this flange brace. As per code, the code says has some requirement that it should be capable of transferring 1% or 2.5% of the forces depending on different condition. So when the compression flange carries a lot of forces, we should actually check whether these sizes of these flange braces are adequate or not. Now let us go to the physical model to understand how the effective length parameters Lx, Ly and Lz should be defined. So that will give a better graphs to you on effective length parameters. As we have discussed in the theoretical part, that we'll take a physical model and try to define effective length parameters and other design parameters of steel building that has to be provided in a STAAD flow. Before we proceed, let me give you a brief description of this building. This building has 5 meter way each. You can look at this. This is 5 meter, 5 meter, then 5 meter. There is a 2 meter height brick masonry, and at the gable end, it can't be seen. It is 6 meter to 6 meter. This is 6 meter. This is 6 meter. So, for our description purpose, we'll take this hub as PB building, and the other hub as the office building. So, see the requirement of a industrial building and a office building usually differ. You can see the flange braces here. The columns flanges are braced through the girds using angles. So these are allowed in industrial building, but these are not allowed in commercial or residential building. And obviously the roof basing, these flange braces of the Rafter, these are called Rafter, the beam at the top. The roof bases are allowed in PAB building as well as residential or commercial building, because in commercial building they usually have a false ceiling, so that this roof bases will be hidden. But in a commercial building, the flange bracing for column part is not allowed, usually not allowed. So let us come to the gable end again. You can see the center to center height of the column beam intersection is 3 meter for the first floor. Then up to the hip, it is 3 meter. Then at the ridge, again bottom is still 3 meter, and the height of the ridge to the center point is 4 meter. So this center to center distances we should remember, because when we will start defining the parameters, effective length parameters, then we will have to multiply this center to center distance to arrive at effective length parameter. Now before we proceed to effective length parameter, we must know something about lateral torsional buckling factor, that's LLT factor, given in STAAD IS 800-2007. That is actually LX parameter or KX parameter of a STAAD Pro. So I'll show two sheets. IS 800-2007 usually is torsional restraint at support flanges are restrained against warping. Warping is nothing but tendency of the flanges to twist. So in that cases, this LLT parameter is 0.85 L. L is the center to center distance of the support or connections. Again the next parameter is torsional resistance at support, but flanges are not restrained against warping. For that, LLT is 1 L. So in general practice, you usually take LLT or LX parameter as 1 L. So keeping that, we remain on conservative side. At time we can take 0.85 L if our design situation demands, but we'll keep on taking LLT as 1 L. So I have put a transparent sheet to show the deck slab. Deck slab, this is shown partial deck slab. This is the deck slab. You can see this, a transparent sheet, and there is a roof bracing. There is a cross bracing on this side, and there is a portal bracing on the other side. See this part, this hub we have considered as commercial building, office building. This is the part. So in a commercial building or residential building or institutional building, usually there will be doors and windows at the base. So usually cross bracings or X bracings are not allowed. So we have to resort to this kind of portal braces. You see there is a movement frame along the length of the building. So this is called portal frame. These are the portal columns. These are the portal columns, and these are the portal beams. So these portals will restrain this frame along longitudinal direction. So we will start with this column. We'll cover all the members of this building. So we will start with this column. First we'll define LS, then LI, then LZ. These are the parameters. These are the parameters which we need to supply to STAAD Pro before giving the design command. One thing, when STAAD takes node to node distance as effective length, if we do not give effective length parameter explicitly. So in case, suppose for this column, this is 3 meters up to this node, there could be a node here. There could be node here at STAAD Pro. So this is 3 meters. So LX parameter of this column is 3 meters. So if we do not give this parameter in STAAD Pro, that is okay, because STAAD will by itself will take 3 meter node to node distance. So we must ensure that there should not be any node between these 3 meters. So if there is no node in between these 3 meters, STAAD will take by itself. So we need not provide the LX parameter for this column. So we can save time following that. So now, what is LX parameter? For this column, we have defined LX parameter. LX parameter is nothing but which will restrain the column from twisting. It could try to twist. Like this, twist like this. Now see, this column, there is a moment connection here. See, end plate connection. This is actually a 8 volt connection, but here we have provided 4 pins because the model is small, so we could not be accommodated 8 pins. So this is a moment connection. So this will actually restrain this column from twisting. So from the base plate, base is fixed. This point is fixed. There will be a stiffener plate along this point. In this model, we do not have a stiffener plate. So for this case, the flanges are also restrained. The wave is also prevented from twisting. So we can actually define 0.85 L as LX for this column, but for usual design practice, we will keep LX as 3 meter, that is node to node distance. So this is our LX parameter. Then we come LI parameter. See, in STAAD Pro, all the parameters are defined. Design parameters, effective length parameters are defined with respect to the local axis. So the local axis of this is the local axis for this column. So you can see there are bolts here, but these bolts are arranged in such a way that this joint behaves as a pin joint about YU axis. Why? See, there is no flange here. So when these bolts transfer restraint, it cannot produce that kind of restraint which can be considered as a moment connection. So you can see, if we come to this direction, there is a flange here, and there is a flange here, there is a flange here. So for this direction, this is a moment connection because flange is contributing. So enough restraint. So we can consider this is a fixed connection, but along YUI direction, there is no flanges. So only these two plates will have some inertia. So obviously this will have some movement capacity, but for design consideration, we usually consider either a big joint as fully fixed or it is fully pinned or fully released. So this about YI axis, this base plate, at the base plate the joint is hinged, and then come to the top, you can see there is a cleat connection here. So this is a simple connection, so this is also hinge. Okay, now again let us go along this beam. There is a brace here, cross bracing. So this is a non-sway frame, as I have already discussed what is a sway frame and non-sway frame. So this is a non-sway frame. So when a force comes here, so this beam provides resistance, and this force is transferred to this bracing to the foundation. So for this is for the case is like this. This is our YY axis. See the green bar shows the axis, so YY axis. So for a non-sway frame, the effective length factor is 1. So for this column, Li becomes 1. Now come to LZ. Now for LZ, you have to consider the local ZZ axis. This is our local ZZ axis. So it is fixed about the ZZ axis. At the top, this is also a fixed connection. This is also a fixed connection. So it is fixed at bottom, fixed at top, but there is no bracing along this. So this is the movement frame. So this is a sway frame. So our case become sway, fixed at bottom, fixed at top, but it is a sway frame. The frame is swaying. The lateral movement of the frame is not adequately restrained. So it is a sway frame. So the factor will be 1.2. So 3 meter into 1.2, 3.6 meters. So our LX become 3 meter, Li become 3 meter, but LZ become 3.6 meter. Now let us come to the top part. Again, going by same analogy. There is a moment connection here. This is providing torsional resistance. So LX will be 1, then Li. YY axis. There is a stud here, which is simply connected. It is not connected to the flange. There could be bolt, but here it is welded. So the forces are moving from here to the bracing, and from the bracing to the foundation. So it is restrained along YY direction. So the effective length factor will be 3 meter. Li will be 3 meter. Again, LZ, come to the LZ factor. So our ZZ axis become like this. So fixed at bottom, fixed at top. So the effective length factors become 3.6, that is 3 meter into 1.2. I already shown it. This is this case. See, this green projecting part is along the ZZ axis. So it's sway frame. So 3.3 into 1.2 is 3.6 meter. Now let us come to the gable column at the middle. This is the column. LX will be 3 meter because pinned at bottom about YY axis. This is top is resistant through movement connection, so there will be stiffener again here, so it is resistant again twisting, so we'll take 3 meter as discussed as LX. Now when we go to alloy parameter, again bottom is pinned, top is pinned. Now look at this arrangement. This is a joist, this is a beam, and there is a transparent sheet which here is representing this is representing the deck slab. So the forces travel here through the deck slab, it transfer to this beam, and through this beam it transfer to the bracing. So the sway is prevented. About this direction, again if you come to this part as well, there is a portal frame here. The portal frame is a sway frame, but with respect to the portal frame, for all design purpose, practical purpose, we can consider other frame which are extended by this portal as non-sway, provided that there should be a gravity column about that direction. So the effective length of this column also becomes 3 meter, that is 1L. This is our case. YY axis. Then similarly, if we come to local ZZ axis, again fixed at bottom, fixed at top, but it is a sway frame, so 3 into 1.2, 3.6 meter. Now let us come to the top part. Now there is a moment connection here, there is a moment connection here, there is a moment connection here, there is a moment, so there is a torsional resistance here, there is a torsional resistance here. So the height of this column is center to center distance is 4.2 meter. 4.2 meter, so our LX become 4.2 meter. Now alloy, I can by same analogy, this is a strut and there is a roof bracing. You can see this is the strut, there is a roof bracing. Now the forces travels here. I provided truss kind of roof bracing. This could be a X bracing as well, but a truss kind of roof bracing or bracing can be also provided in structures. So the force will travel to foundation through this portal frame and through this X bracing. So this column, for this column about local YY, the top part is hinged, but it is resistant against translation. Translation means the translation is being prevented through the roof braces and the strut and the braces at both sides. The translation of this column is resistant through this strut, then through the braces at the roof, and then the forces goes here to the foundation, then the forces goes through the portal frame through the foundation. So it is non-sway frame. So the alloy parameter also remains 4.2 meter. Now again comes to the LZ parameter, fixed at bottom, fixed at top. So again sway frame, no X bracing or cross bracing here, or any kind of eccentric brace of it itself is a portal. So when portal moment frame resists a lateral load, it itself has to be considered as a sway frame. So this is a sway frame. So 4.2 meter into 3.6, 1.2. So the effective length of this column becomes 5.04 meter. So LZ is 5.04 meter, LX is 4 meter, LX is 4.2 meter, alloy is 4.2 meter, but LZ is 5.04 meter. For this column, there is a restraint, there is a mid landing beam here. You can see this mid landing beam. There is a mid landing beam here at the middle of the strip. So, but the connections are pin connection. A cleat connection is here. You can see this cleat connection. There is a cleat connection, simple connection. So it is hinge at bottom about LI direction, hinge at top at LI direction. But when we consider LX parameter, so LX parameter, there is a cleat connection is there as 1.5 meter height. So we cannot consider this LX, this cleat adequate enough to restrain the twisting of this column. So for this column, the LX will be 3 meter. For this column, the LX will be 3 meter, but then LI will be 1.5 meter. Note that the LX is 3 meter, but the LI is 1.2 meter because there is a mid landing beam here. So this force get transferred to this column, and there is a portal base ahead of this. So the lateral forces get transferred to the portal braces through this arrangement of all these columns, the portal frame as well as the movement frame here, this movement frame, and the portal frame, this column. So you can see there is a portal frame. So obviously the forces will be transferred to the flexural action to this portal, that is moment action through this to this portal. The forces will be transferred to the foundation. So LI is restrained. So LI will be 1.5 meter for this column. Now come to LZ. LZ parameter. Again, it is a sway frame. 3 into 1.2 is equal to 3.6. For this column, LZ is 3.6 meters. So our one frame is complete. Let us come to the second frame. There is a movement connection here. This is the movement connection. So the column is restrained against torsion and twisting. So the LX for this column will be 3 meter. Again, the forces about LI direction. It is pinned about this direction. It is pinned. There is a cleat connection here. There is a cleat connection here. So this is a simple connection pinned at about this direction. But there is a basing here. So this remains 3 meter. So LI is 3 meter. Again, LZ is 3.6 meter. For upper part also, the same cases is there. Now, let us come to the column on the other side. For this column, LX is 3 meter, LI is 1.5 meter, and LZ, there is a moment connection here. There is a moment connection here about ZZ axis. This is our ZZ axis. ZZ axis. So there is a LZ becomes 3.6. Same cases here. LX is 3 meter, LI is 3 meter, and LZ is 3.6 meter. See, for lower part, LI is 1.5 meter, but for upper part, LI is 3 meter. Now let us come to this portal frame. This is the portal frame. It is tapered. There is sometimes some bolts are provided here, sometimes it is not provided. It is simply left as it is on the base plate of the main frame. So this is a pin connection. This is pin at bottom, fixed at top. It is a portal itself which is resisting the lateral force. So this is a sway frame. So we have to consider the case. Pinned at bottom and fixed at top. But before that, we must discuss about the LX parameter also. So LX parameter remains 3 meter. There is a lateral torsional resistance here. There will be stiffener here, so torsion twisting of this portal column is prevented. So LX is 3 meter. Then if we consider LI, so LI we can define it as 3 meter for this portal frame because there is a moment connection here, but this is connected to the main frame, so we should not consider. If you see, there is a moment connection here for this main frame attached to this portal frame, but we cannot consider this moment connection providing fixed to about YY direction of this portal frame because it is not connected to the flange of this portal frame. So we can consider this as providing a simple resistance. So LI will be 3 meter. Now why 3 meter? Because this is the main frame is a sway frame. Then how can we take 3 meter? Now I told for this portal frame when we consider YY direction. Now this about the YY direction, this main frame is actually acting as a portal frame. So for a practical purpose, we can assume this main frame is extending this portal frame about YY direction. So this is 3 meter. See, actually, a portal frame is a sway frame. So sometimes secondary analysis is required whether we can take whether we can consider a portal frame providing adequate lateral strength to a column so that we can take its effective length as 1. But IS code does not elaborate much on this AIC, but there is some elaboration on the AIC code. So it says in secondary analysis the lateral deflection does not exceed more than 10% from the prime first order analysis. So we can always consider the effective length of the column it is providing resistance to as 1. So for this column we have LI is equal to 1. So 3 meter, LX is 3 meter, LI is 3 meter. Now let us come to LZ parameter. This is ZZ axis, local ZZ axis of this portal frame. So look, this is pinned at bottom, fixed at top, but the portal frame itself is a sway frame. This portal frame itself is a sway frame. So when a force comes from these directions, this tries to sway this way. So pinned at bottom, so the effective length of this particular portion up to this floor will be 2. So the effective length of this column about LZZ, about local Z will be 3 into 2, 6 meter. Note that this will be 6 meter now. Now if we come to the top part of this portal frame, fixed LX again 3 meter, LI with same concentration as below. LI is 3 meter, LZ fixed at top, fixed at bottom, but sway frame. So for a sway frame, it is with fixed at top and fixed at bottom. The effective length factor is 1.2, so effective length becomes 3.6 meters. Almost same is the case for this frame as well, this portal frame. So this portal frame and this portal frame will have similar parameters. Now let us come to the last frame, which is a bit different. Let us move this brick wall a bit away. We have not yet considered the PEB part. We are discussing in sense of a commercial building. So I will let you know what will be the things in PEB building. So this is LX. You see, the connection here is through a end plate. Now this end plate is adequate enough to restrain this column. I have already told you that when the flanges are strained, when there is a torsional and flanges are not restrained against arming, effective length factor can be taken as 1. So this remains 1. So LX is 1. Again, by same analogy, the forces LI will be through this strut. LI forces will travel to this bracing and to the foundation. So it is restrained against sway. So LI is 3 meter. That is 1L. This is our LI. For this column, there is a cleat connection. So it is one. There is a portal frame. This itself is a portal frame. There is a cleat connection here. So this is not providing any fixity here. So this is bottom is fixed about ZZ axis. Bottom is fixed about ZZ axis. Top is not fixed, so bottom is fixed, top is pinned, and this is a sway frame. So when this is a sway frame, so again our case comes. Now look at this. I am just inverting the figure which is given in the code. Inverted that figure. Bottom is fixed, top is pinned. Actually it is top part which is swaying, but for assumption we can consider this part is swaying, considering this top part is here and the fixed part is swayed here. So this become 12. So for this column, this is about local ZZ axis. The LI will be 3 into 2, 6 meter. Again for this column, our usual portal case comes. Bottom pinned, top fixed. So same will be the case here for this column. There is a expressing, there is a portal brace here. So I told you portal brace itself will be considered as a sway frame, but for the other part we can consider it is a they are the non-sway columns. They are basically gravity columns about the directions. So there is an end plate for this STAAD. So this will provide lateral restraint, torsional restraint to the wave twisting of the column. The flanges are not restrained, but we can always take as one. So LX is 2 into 3, bottom fixed, top released, 2 into 3, 6 meter. For top part also it's remain the same thing. Now this is the columns which needs special consideration. Now look at this column. This is pinned at bottom about both the direction. Pinned. Now this column is for LX. There is if you see it here, for these studs are provided with end plates. So these are providing restraint upon twisting, but the flanges are not restrained. But we can always take 1L. So LX will be 3 meter. Then alloy. This is our local alloy axis. So now this for alloy axis, this is the about alloy, local alloy. This is the gravity column. So restraints are being provided by this portal frame. This is now acting as a portal frame. This column, this providing lateral restraint to this column. So alloy will become 1L. So this is 1L again. So 3 meter. Now let us come to LZ. Now fixed, pinned about local ZZ axis, pinned at bottom, pinned at top. You can see this connection. Can you see this connection? The bolts are within the flanges. It is not outside the flanges. So this is actually pin connection by design assumptions. But this pin is being restrained at the top. So the forces are traveling here. The forces are traveling here to the roof braces, then to the foundation through the eave braces. Now note that there is no member. There is no member here at this floor 3 meter level to provide a restraint. So the about local ZZ axis, the length of this effective length will be 3 meter plus this we have discussed 4.2 meter. 3 meter plus 4.2 meter is equal to 7.2 meter. Now this is the height we have to consider. Restraint at the top, restraint at the bottom, but pinned, so it is 1L. Now we are left with the interior columns. Interior columns again. LX is 3, alloy is 3.6, LZ is alloy is 3, LX is 3, alloy is 3, and LZ is 3.6. This is the case. Again for the other interior column here, if you can see this column, this is again, if I put the local ZZ axis here, so LX is 3, alloy is 3, but LZ it is along a sway frame, movement frame. It is so 3.6. So with this we covered all the parameters of the columns. Now a special consideration. Now for a PEB building, this was our brick machinery here. For a PEB building, the flanges, the girts and the roof braces provides flange braces to the compression flange of the wave. Now in such a case, these girts or these purlins actually provide restraint to alloy and LX. So in case of a PE building which is provided with the flange bracing, the effective length parameter will be distance between the flange bracing. So suppose these girts are provided at 1.5 meter center to center. So for these girts I have shown only the partial girts. So these girts could be here up to this point, then here, then there will be girt. So this will be if they are 1 point, so LX and LY will be 1.5 meter. But see now, see there is a 2 meter brick wall below. So for the first 2 meter, LX and LY will be 2 meter. But thereafter the LX and LY will be 1.5 meter. But LZ parameter will remain as I have already discussed. So let us come to the Rafter now. So if you can see the flange braces, if these purlins are provided with providing flanges to these braces, LX and LY will be center to center between these flanges, that is one. If they are as 1.5 meter center to center, LX and LY will be 1.5 meter. But the LZ parameter. Now see, we have to consider there is a kink here, and I can consider this joint similar to the joint here. So the LZ will be half of this. This is a fixed. This is a fixed. For so this is a fixed joint, which is there is no joint at all, but it's really materially fixed. So the LZ parameter will be half of this. So we can take LZ as per slope 6.1 for this Rafter, but if there is no, for this Rafter also 6.1 meter slope wise, if you calculate the length, this length is 6.1 meter. Now if suppose there is no flange braces, what will be the LX and LY? Now there are resistance at this point, at the half of this. So 6.1 meter divided by 2 is 3.05. So LX and LY will be 3.05 if there is no flange braces. Same is the cases here. Same is the case for this part. Now let us come to these beams. First consider the main beam parallel along the building. So this is a simply supported beam. So it has a deck slab. So deck slab is actually holding the compression flange. This is also simply supported beam. If you remove this brick wall, this is a simply supported beam. So see, in LX parameter, AIC code says the torsional resistance can be at any level. It need not to be near to the compression flange. So LI, obviously for LI parameter it should be near to the compression flange. So for this, the LX and LI we can take the screw spacing. Screw spacing is usually double the corrugation of the deck sheet. If we consider a 130 mm corrugation to corrugation distance for a deck sheet, so the distance LX and LY will be 130 into 260 mm. But for all practical purposes, we consider one screw could be loosened, so it will be double of that. Usually the screw spacing are considered as 300 for considering various type of deck slabs. So 300 into 2 is 600 mm. So we consider LX LY as 0.6 meter, and LZ will be 5 meters. See, I am taking 1L 5 meter. This is, it cannot sway along the vertical direction. Obviously, there is a steep foundation there, so we can always consider it is a non-sway. It is braced against vertical direction. It is sway is prevented along the vertical direction. So this is 5 meter. LZ is 5 meter. Same is the cases for the joist as well. If you consider this beam, this is also simply supported. This is also simply supported. So all these beams are simply supported. So we can consider this. Now there is a special case for these two beams. See, there is no deck slab for this. So there is no. Obviously there will be some deck slab here, but this stringer will provide adequate restraint, so we can leave it to this LXLI parameter as per STAAD. The distance between the stringer, say suppose it is 1.2 cm, say it is 2 meter, so we can leave it as LXLI as 2 meter, but LZ will be 5 meter. This beam LZ is 5 meter. For this landing beam also LZ is 5 meter. For this beam LX, LY, LZ all are 5 meter. But for this beam LX, LY we need not to define it. We will start to but the maximum is LX, LY is, if the stringer is split as 2 meter, then maximum LX, LY will be 2 meter. So now let us come to this portal frame. This is the beam. So actually British code allows point of control fracture to be taken as torsional restraint, but American AIC code says exactly opposite, that AIC code says the most vulnerable point. So we should take the whole length as LX, LY, LZ for this. For any practical purposes, if we actually want to economize, we can provide a beam at the center connecting to this joist, and then the effective length LX, LY will be 2.5 meter if we provide a beam here along this part to this joist connecting a simple beam, so that will provide restraint. So in that case 5 meter divided by 2, LX, LY will be 2 meter, but LZ will remain 3 meter. Now for this case we cannot provide any top beam, so for this beam LX, LY, LZ all will be 5 meter. Now let us come to the frame beam. This is the frame beam. For this frame beam, there is no restraint. So LX, LY, LZ everything will be 6 meter. For this beam, LX, LY, LZ. Now see this beam. I have told you that for a simply supported beam we can take LX, LY as 0.6, but this is not a simply supported, this is a fixed beam, so there will be point of contact fracture. But for a fixed beam, if you can see this joist below the deck slab. For a fixed beam, we can take LX, LY as the center to center distances between this joist, provided this joist cleat connections. You can see the cleat connection here. Cleat connections extend beyond the half of the main beam, main girder. So this is 6 meter. There we have two joists here. So the joists are spaced as 2 meters. So LX and LY will be 2 meter, but LZ will be 6 meters. So for all the cases here, for this beam, LX, LY 2 meter, LZ is 6 meter. Now let us come to the stringer. Stringer is simply supported beam. It is a cleat connection here. See, we must provide a slotted hole here or some here, so that it does not take part in resisting lateral movement, because it is a cross type of member. So if you leave it like this, it will obviously start obstructing lateral forces, and we should not let the staircase to do that. Staircase is one of the main elements for escape of people. So we must provide a slotted hole here during or releasing the fabrication drawings. So these are simply supported beam. For a PV building, this will be provided with steel thread, which will be obviously the threads will be provided with angle support. So that will be around 300 mm. So we can consider. And for in case if there is a deck slab, the screw will be also spaced as 300 mm. So for all practical purposes, we can consider LX, LY as 0.6 meter, and LZ the total length, horizontal length. See, I am talking about the horizontal length, not the length of the member. horizontal length of this stringer. Suppose this is from this to this point. This to this point is 5 meters, so LZ will be 5 meters. So now let us come to the STAAD, and this STAAD and braces wall will, the factor will be node to node distance. Which actually, if there is no node in between, we did not to define in STAAD. See, if you see at this bracing, there is a connection here. There is a connection here. Connection here. But while modeling in STAAD Pro, we do not intersect these members. It will create stiffness warnings because there will be problem in the solving the stiffness matrix. So, for design purpose, this is a continuous member, and for this also a continuous member, and the effective length factors remains same. So with this, we have covered the effective length factors of all the members. I hope you will be able to apply in practical design on the concept you have learned. Now let us move to the STAAD Pro again, and we'll define other parameters in the STAAD Pro itself, like yield strength, then ultimate strength, then there will be slenderness limit, etc. that we can discuss in STAAD Pro. So obviously, the whatever factors I have discussed with respect to these buildings, we will have to apply the same concept, the building we are designing with STAAD Pro. With this video, I hope you all have learned about the effective length parameters, LX, LY, LZ that has to be supplied to the STAAD Pro software. I have seen many people are viewing my videos, but I'm not getting much like. So if you like this video, please provide your comments and please like this video. I would like maximum likes from you people. That will keep me energetic and provide enough energy to, it will supply enough energy to myself to keep on posting new videos, new tutorials. In the next sections, we shall apply this design parameter to the STAAD Pro model. So let us see you in the next section.